Hello and welcome to a flipped class on motion graphs, and we'll be looking at more complex motion graphs and how they tell a story and try to tease out the story from the graph. Now, there's a good way and a not so good way of dealing with motion graphs. The not so good way is to try to memorize every single shape and match it to a corresponding motion because there are just too many of them. It'll drive you nuts. The much better idea is to understand how motion graphs work so you could look at them, make sense of them as you're reading them, and figure out what's going on. So the first step for looking at any motion graph is to look at the axes, because position time graphs and velocity time graphs are both incredibly different, and they have different rules, and they will have different motions. So the big first step is to look at what kind of graph you've got in front of you. We're going to start off by focusing on position versus time graphs. So let's take as our sample a position time graph. This one is somewhat non-trivial. We want to tell a story about what is going on in this with this motion. So let's suppose this is, say, a motion of a car, and it produces this position time graph. What did it do? And figuring this out is a lot like analyzing a rather challenging piece of literature like Shakespeare's The Tempest. You read it the first time through, and maybe your first questions are, what is going on here? What is the plot? Who are these characters? I'm confused. And you try to just get a general handle on what's going on. And then as you revisit it, as you look at it again, you can go deeper than that. You can then ask better questions about what, not just what is the plot, what's going on here, but some character motivations and other nice literary stuff. And we can do something similar with motion graphs. So let's do it. Our first look at this is we can say what's happening with the position as time marches on. So the way they read these graphs, time marches on in this direction, and then we can see what's happening with position. So first glance is that as time goes on, the position gets bigger and bigger and bigger. So this thing is moving forwards. Okay? We don't really know any details about how it's doing that, but it's moving in the forward direction. Great. The other thing to look at here is that there are actually three different kinds of motions. There's this upward bend here, there's a straight part, and there's a downward bending. And those are going to be three different and distinct types of motions. All right, so we've done our first reading of what roughly is going on. Let's take a closer look. So the position starts at 0, and it's going to get bigger. You can imagine, if it helps you, if you put numbers on this, you've got 0 meters here, 1 meter, 2, 3, 4, and so on and so forth. So in this first one here, the position is getting larger. And one of the key ideas of position versus time graph is that the slope is equal to the velocity. So the slope right here is very small, and then the slope is increasing. It's getting steeper as time marches on, which means your velocity is getting bigger. So what do we call it when as time marches on, the velocity gets bigger? We call that speeding up. And that's the first part. Now for the second part, the slope remains a constant. It is the same steepness all the way up. Therefore, it must be going at a constant velocity, since the slope is the velocity. And finally, now, as time marches on, you have a very big slope right here. It's very steep. And then as time goes on, the slope is getting less and less, which means your velocity is getting less and less. And that means you must be slowing down. And that's our story. So maybe if we want to put this in prose, light turns green, the car speeds up, drives a little while at a constant velocity, and then slows down to a stop for the next red light. Now let's focus on velocity time graphs. So here's some maybe perhaps intimidating looking velocity time graph. Let's first try to make sense of this. And I think the easiest way is to put some imaginary values on these numbers. Remember to think this is based on actual velocities. So maybe this starts off here at well, it can't start off at 0 meters per second because 0 is way down here. But let's say it starts off at, say, 10 meters per second. So why not? Now, when it comes over here, it must be at some bigger velocity because it's up higher. So maybe that's 12 meters per second. And then when it goes down here, oh, this must be 0 meters per second because it's on the time axis. Okay, so that gives us a little bit of something. It's moving here, it's not moving there. Now let's be a little more specific. And remember that the slope of this line, because the velocity time graph, is the acceleration. Here, your velocity starts at some number and ends at a larger number. That would seem to indicate that you're speeding up. And lo and behold, it has a positive slope, so we must have a positive acceleration. So you're accelerating. Here, your value of the velocity is staying constant. The value here doesn't change. Your slope is 0. That must mean you're going at a constant velocity. And finally here, your velocity goes all the way down to 0, so you must be slowing down. Indeed, you have a negative acceleration. And finally right here, you're at rest. Okay, that's all. Oh, say hi to my daughter. Say hi, Rowan.
Hi.